Now we're going to look at more examples where we will see how we can use different techniques of differentiation to solve problems. So for the coming problems, we're going to look at this technique called parametric differentiation, and we're going to see how we can use that to solve different kinds of problems. So for the first example, let's consider the question here that asks us to find the gradient at an arbitrary point T on the ellipse specified by the following expressions, where we have x equals to a cos t and y equals to b sine of t, given that the range of t lies between 0 and 2 pi. So we're going to find the gradient, and as we already know that the gradient is specified as dy by dx, and using the chain rule we can simply define it as dy by dt multiplied by dt by dx, and then we can just go ahead and write it like this, where we have dy by dt divided by dx by dt. So one thing to note here that is important is you see that we are differentiating y and x with respect to t, and that is because the expressions that are specified here on the question of x and y are functions of t only. So it's important that we differentiate it with respect to t. So now differentiating y first with respect to t, we get b cos of t in the numerator, and this will be divided by the differentiation of x with respect to t, which is simply minus a sine of t, and then this finally gives us the answer, which is minus b by a cot of t, given that our expression for sine t is not equal to 0, because we have sine t in the denominator, and for in fact the values at which sine t is equal to 0 is t equals to 0 plus minus pi plus minus 2 pi, and in fact these are the points at which the tangent to the ellipse is parallel to the y-axis. So we found the gradient of the ellipse at an arbitrary point that is specified by x and y. Now we're going to look at another example where we will see how we can use parametric differentiation to solve it. So the next example has the same values of the ellipse, where we had x equals to a cos t and y equals to b sine of t, and the range of t is the same. But for this question we are asked to find d square y by dx square, which is the second derivative. Now we're going to use parametric differentiation to solve this, and we recall that d square y by dx square is actually d capital Y by dx, where we can just define capital Y to be dy by dx. So differentiating capital Y with respect to dx will just simply give us d square y by dx squared again. So applying parametric differentiation, we have d squared y by dx squared, this equals to dy by dx. Again we can break it down with respect to t, because we're changing the parameters here, which is why it's called parametric differentiation. We're changing the differentiation from dx to dt, this divided by dx by dt, because this will again eventually give us dx squared by d squared y by dx squared. So now moving on by differentiating. So first of all, we see that capital Y equals to dy by dx, which is exactly what we found in the last problem. So we can go ahead and substitute that. So we know that dy by dx equals to minus b by a cot of t. So differentiating this, will give us dy by dt, basically differentiating it with respect to t, and this will give us minus b by a cosec squared of t. And then we know that we need to also find dx by dt, which is simply the differentiation of x with respect to t, which is what we also found in the last example. So this is simply minus a sine of t. Now putting these values into substitution in this expression here, so we have dy by dt as minus b by a cosec squared t, this multiplied by minus a sine of t. Now this gives us the expression minus b by a squared sine cubed of t. As we know that cosec square is basically 1 by sine squared, and we also had the denominator to be sine of t here. So what we get is minus b by a squared sine cubed of t. This is the final expression for d squared by dx squared. So I'm going to write it here. So we get d squared y by dx squared to be this expression here, which is what the question asks us to find.